the sun's awesome furnace. From the deep bowels of the earth, nature's elemental forces have raged long before man's coming. Over the eons, man has feared their erratic, destructive power. He has offered up prayer and sacrifice to wrathful gods of sea and wind, to the deathly chill of the oncoming ice, to the torrential floodwaters, and to the terrible twisting force that dropped from the heavens. Then man began the slow turn away from witchcraft and superstition to the discipline of science. He fashioned crude instruments that set him on the path toward understanding the riddle of the elements. He developed ways to measure the relationship between the wind, temperature, air pressure, and moisture content of the skies. From the minds of Galileo, Torricelli, Fahrenheit, Celsius, the science of weather began to develop. And by the 19th century, a rough record of scientific prediction began to emerge. Today, those who keep an eye on weather's uncertainties have more sophisticated devices to record, to track, and to predict the behavior of the elements. Using computers, advanced sensors, and other tools of the space age, they seek to narrow the range of nature's secrets. And like those here at NASA's Goddard Space Flight Center, they are deeply engaged as the latest in the special line of professionals, the weather watchers. In our day, the weather watchers not only searched the heavens for signs, but launched sensitive eyes in the sky to scan the Earth in its atmospheric patterns. Since 1960, when the first orbiting weather satellite was launched by NASA, the United States has advanced its meteorological observation, information, and sensing systems. From the beginning, the scientists realized the limitations of their data gathered by polar orbiting satellites. They could scan a developing weather system only once every 12 or so hours. They looked for ways to keep a sharp eye on the same segment of the Earth around the clock. Starting in the mid-1960s, a series of geosynchronous satellites was launched. Riding in stationary orbit relative to the Earth's rotation, they can maintain a constant data-gathering vigil from 36,000 kilometers above the Earth. Improved resolution and infrared imaging devices were developed for subsequent satellites, adding to the refinement of the art of weather watching. By the late 1970s, in cooperation with European, Japanese, and Russian meteorological agencies, there will be 5 geosynchronous satellites providing general weather data on a constant basis from almost every corner of the globe. The weather watchers of today all across the country feed us a constant stream of updated readouts and predictions about tomorrow's weather. Many, however, are research specialists trying to cut down the odds on nature's surprises. One of these specialists at NASA concentrates his attention on hurricanes and severe thunderstorms. Bill Schenck.
We hope to improve the prediction of tornadoes. We think right now that the first step in this is being able to identify which areas later in the day severe thunderstorms will form that will predict or will generate tornadoes later. Once the cells have formed, we like to think that the best method is to take a probabilistic approach, either with regard to a specific point on the ground or a specific cell as to the potential of that cell producing either tornadoes, hail, or other types of severe weather.
This team is part of NASA's Severe Storms Research Program, and they don't spend all their time in the laboratory or by a computer. They are working on a cooperative experiment between NASA, NOAA, Colorado State University, and the University of Chicago. Each year, during the peak period of severe storm activity, they pinpoint a likely trouble spot.
Rapid development southwest here in Stephenville, Brownwood area.
How far do you think that area is out there, Ed?
It's just about 150 miles or so.
150 miles?
I think.
And they get set to go out and eyeball it, close up, firsthand.
Tornado will go out at about 5,000 feet, and the Queen Air about 15,000 feet at the measurement level.
They go by air. A prop-driven T-28 leads the way. The Queen Air, with special sensors, will work at medium altitudes when they all meet, in Bill Schenk's words, at the thunderstorm. A Learjet will work the highest level of the storm cloud, or cell, as the meteorologists call it. Working as an airborne observational laboratory, the three planes, with scientists aboard, will box and record the key elements of the developing storm. The T-28 will monitor the bottom of the cloud at around 5,000 feet. The Queen Air will take its measurements at the storm's mid-level, around 15,000 feet. At the boiling and swirling top of the anvil head itself will be the Learjet. Riding inside is the coordinator of the mission, Bill Schenk.
What you end up doing is combining the data from all three aircraft to see if there's a number of parameters whose conditions are all satisfied when a particular type of weather event occurs. Say if a tornado occurs, perhaps you have the collapse of the top, very strong inflow at low levels, and also perhaps some changes in the temperature and moisture structure on the upwind side of the storm. The current geosynchronous satellite measures parameters connected with the cloud structure, the cloud height perhaps, the cloud type, and can measure or infer the wind velocity from the movement of the clouds. It's a combination of the aircraft validating the satellite measurements and the aircraft complementing the satellite measurements.
352 radio at about 16 miles.
Okay, I understand. Where are you now?
I'm on the Lomita 166 radio.
The forces that produce the tornado cyclone are still one of the great mysteries in meteorology.
Research data yet?
One thing that we've noted over the years is the presence of curved lines of clouds that are moving towards the main storm, and these are often a reflection of the circulation in the lower atmosphere. The main thunderstorm can act as a partial obstruction to the flow and create boundaries which perhaps can lead to the rotation within it.
There is new growth occurring on the southwest flank of that cell.
We are studying the circulations in the lower atmosphere to see how the rotation gets concentrated in such a small area to produce the tornado. We have noted also a collapse of the cloud tops during the period which the tornado is produced. This factor, along with others, perhaps can lead to a better tornado detection and forecast system.
You said no. Okay.
The airplane photographs from the Learjet, since they are higher resolution and more frequent than the images from the geosynchronous satellite, serve as a way of examining in greater detail what the satellite is seeing and giving us a better interpretation of satellite data.
As the storm develops, additional data will be gathered at ground stations to supplement and refine what the aircraft and satellite findings will tell them.
Radar helps us, along with other sources, in the decision on which cells are the most severe. For example, a hook echo is an indication that the thunderstorm has rotation and indicates that the storm is becoming tornadic or is tornadic. There's also a lightning measurement device on the Queen Air, and it will relate the intensity and frequency of lightning strokes. to the type of weather being produced in the storm, whether it be a tornado or hail or just heavy rain. People will call something a severe hurricane or a severe thunderstorm, and there are various classes of these. The key here is to measure them at the right place, at the right time, and with the right frequency.
Trying to predict when and where tornadoes may strike is just one part of NASA's ongoing storm research program.
At NASA, we're involved in tropical cyclone research as well as severe local storm research. Right now, we have a tremendous lack of simultaneous data of the wind field at both at low and high levels in a hurricane. The aircraft make measurements going in and near the center and then flying back out again. And it only covers a very small fraction of the total circulation of the storm. Whereas by taking images more frequently from the satellite, we can get much more information within the interior of the storm circulation.
The ultimate goal we're trying to do is to improve the detection and prediction of severe local storms, tropical cyclones, and then other weather features that people often don't associate with being storms, such things as dust storms, fog, frost and freeze prediction. And then we'd like to just understand more about these kinds of atmospheric processes as well, which should ultimately feed back into a better detection and prediction capability.
The computer continues to be the chief tool of today's weather watchers. After each mission, its arcane images and language give them some new answers and some better questions about severe storm behavior for the future.
It's pretty obvious from the data, I think, that you can make some quantitative estimates of parameters that are associated with both cloud growth or thunderstorm growth and also what's happening on the top of dense cirrus shields.
It may take weeks, it may take years, but NASA's weather scientists carry on a constant dialogue of analysis and interpretation of the data they gather with a scientific wariness of coming to an easy set of answers.
Interviews of the people on the ground. There's so many different ways to make mistakes about a tornado situation.
The uncertainties of nature that held the ancients in awe are slowly being understood. In the coming decade, new satellites will show us weather conditions in finer detail and at faster rates. Advanced aircraft sensors will probe inside as well as around storm systems. To solve the inner mysteries of the world's weather is the challenge of NASA's scientists, a challenge which its weather watchers have dedicated their machines and minds to pursue day after day after day.